Hey guys, um, so I'm gonna take this course in 12 days, 11 days, and it's programming, technically. Well, there is programming. So, since my GPA went down the shitter this semester, having overloaded my schedule, I think we can kill two birds with one stone and prepare ahead for this course, but still fall within the bracket of programming every day, right? So I hope you don't mind that I sort of switched up, but this is more like computational mathematics, and that's what I'm very interested in, and that's what I eventually want to go into, like simulation, computational physics. I think that's that's my interest, and my ultimate end goal is to um apply programming to solve like physical or mathematical problems. So we should I figure why don't we just go through this line by line and get to the get to the bone of this. And then that will also serve me as a witness to whether preparing ahead of time like this will actually help me during the actual course. I mean, obviously it will, but I do want to understand to what degree, and if this turns out to be successful, then I can apply the same sort of strategy for my upcoming courses in the fall next year. But I'm not going to record those, but just to test the method of, studying ahead for a course here. So this website it's a really pretty one, and yeah, so this is Math 307 Applied Linear Algebra. And so the learning goals for this course are to summarize properties and constructions of matrix decompositions, LU, QR, and SVD. Absolutely no idea what that means yet. Perform matrix computations using mathematical software, Python, SciPy, and Jupyter. So we do know what those things are. Compute solutions of linear systems of equations using matrix decompositions. Compute least squares approximations of linear systems of equations using matrix decompositions. Okay, so solutions of linear systems of equations, least squares approximations of linear systems of equations. What does this mean? Oh, wait. Oh, it's linear regression. Okay. Approximate eigenvalues of matrices using iterative methods. Okay. Analyze digital signals using the discrete Fourier transform. All right. So, okay. There's no like introduction to this. Oh, I forgot to start this. Math 307. I just want to sort of see. Seems like there's a website, like different websites. This is a very different. How old is this? Okay, the lecture goals are course goals are the same, but these are. That sounds different. Homework. 307. Okay, what is this? Oh, that's the GitHub. Can't reach that. Nope. Whoa. This is cool. Um, this is very cool. I'll save that. All right, LU decomposition. Big idea. Record the row operations of the Gaussian elimination algorithms in the LU decomposition and use the decomposition A equals LU in backward forward substitution to efficiently solve a system of linear equations AX equals B. Okay, still don't really understand. Decomposition. So we want to efficiently solve a system of linear equations. Okay. Gaussian elimination. We learned this in 221. Definition: a linear system of equations is a collection of equations of the form this, where the coefficients are known and x is the unknown variables. A and B are known, but x is the unknown. Matrix notation: linear system AX equals B is built like this. A times X equals B. And we know A and B, but we want to find X. This is great review. Okay, definition. There are three types of elementary row operations. You can interchange two rows, multiply a row by a non-zero number, or add a multiple of a row to another row. Definition: a matrix is in row echelon form if all zeros rows are at the bottom. The first non-zero row. Yeah, okay. Row echelon. Row echelon. Yeah. Let A be the matrix and let U be a matrix in row echelon form obtained from A through sequence of elementary row operations. The rank of A is the number of non-zero rows, and U denote the rank of A by rank A. Hold on. I just want to see quick when we get to code. Because I don't see. Oh, I see. It's right here. So, wow. Okay. Okay, so I'm gonna guess that we read the theory first and then up do the Jupyter notebooks after. So interpolation, differential equations will involve the finite difference method. Orthogonality. Okay, I know like least squares approximation should have some. Yeah. Okay, so we'll read through this. I just wanted to sort of understand like when the coding part comes in because I just keep seeing these questions and they're all math. All right. Let's open up some notes. The notes. I like I don't want to spend too much time on it. I just, you know, I just need if I need a decomposition stuff I sort of know I think I need a reminder on. Uh yeah, like definition, rank A is the number of non-zero rows in K. Let U be a matrix and row echelon form which used to be matrix A in U. Feel like this is kind of I'm a little sad I can't bold the text, the math, but it's okay. Definition Let A equal be an m by n matrix with rank A equals R. The system AX equals B is inconsistent. Hold on. There we go. That's better. Feels so cluttered. Okay, the system AX equals B is inconsistent, i.e. no solution if rank of A is less than the rank of AB. In other words, the rank row echelon of form of the augmented matrix AB has a row of the form. Okay. Definition. Inconsistent and consistent matrices. Systems. Equations. A system AX equals B. Okay, I want to use when there is a no solution. Row echelon form of the augmented matrix. What is this? Oh, I see. Has a row of the form um 0 0 to dot quad 0 1. How do I want to make okay. Infinitely many solutions. As infinitely when rank A is smaller than equal to when rank A equals rank AB, but it's but less than the number of variables in the system. So they're gonna do elementary row operations. So add -1 times row 1 to row 2, and add -2 times row 1 to row 3, and 3 times row 2 to row 3. Okay. Since there's no leading 1 in column 3, assign the free variable t to x3. The second row implies wait. Add 3 times row 2 to row 3. Since no leading 1 in column 3. Okay, so there are infinitely many solutions. So if we make x3 the free variable, so x3 equals t. Oh, so we can write all the other variables in terms of t. So x1 is equal to 2 minus x2 minus x3. But since x3 is equal to t and x2 is equal to 1, we have 2 minus 1 minus t, so it's 1 minus t. And if we look at the second row, we see that x2 is just equal to x2, so it's 1. And then the third row is t is the x3 is t, the free variable. Okay. Moving on. Find the solutions of ax equals b, where a equals this big matrix and b equals this. Wait, is this where we use the Jupyter notebook? Mm-mm. You know what? Why don't we boot up Jupyter Notebook and just try to code these up ourselves right now. Math 307. So, file, open, or 307. AU decomposition dot ipy notebook. So why don't we try the first simple example? So we can say example one. Let's see how this is done. Oh, port numpy as mp. This is markdown. As LA import matplotlib dot pyplot as plt. Okay, so linear systems of equations, ax equals b are solved by we create numpy arrays to represent a and b. Then we compute the solution x using the scipy function scipy.linealgebra.solve. Alright, I'm tired. I'm thinking I'm gonna call it today, but we're gonna work more tomorrow.